All right, I've made the claim in the past, and it's a true claim, that for every conservative force, there's a potential energy formula. So if we have this conservative force, if the conservative force is weight, then the potential energy formula associated with that is mgh. Weight, any gravitational force where the acceleration does not vary greatly. If we're talking about the generalized gravitational force, in other words, the g m1 m2 over r squared, then the potential energy formula associated with that is negative big G mass 1 mass 2 over r. I'm not going to derive this formula. It does require calculus. However, just trust me. If the formula is the elastic force, this is equal to mg. If we're talking about the elastic force, let's not worry about vectors at the moment. Or I put an S down here for spring, then we're dealing with kx. If we run the vectors, there'd be a negative sign in there. And then that would correspond to 1/2 k delta x squared. I guess that should be a delta x. And then those are the three main ones for 151 and 251. But this is the one we care about. So if I have a planet, some planet X, and I want to launch something off the planet so that it goes away and never comes back. The question is, how fast do I need to shoot this in order for it to go? So I have some object here, which I'm going to call mass sub 1, and then this has a mass of x. Now, because it is going to be traveling a great distance from the planet, the force is not constant, so F equals ma becomes a little bit trickier. We could use F equals ma with calculus, but without calculus, using F equals ma becomes incredibly tedious because you're having to do small increments, and you just do a bunch of iterations, and eventually you get somewhere, assuming your iterations are small enough. So, well, that's the essence of calculus, isn't it? You do an infinite number of infinitesimally small things. All right, so as we're launching this, the only force acting on it once it has been launched, if we did a force diagram, it would be the force due to gravity. It is acting back towards the planet. The velocity of the object is to the right. The force of gravity is to the left. They are in opposite directions. Since the force of gravity is to the left, the acceleration is to the left, which means it is slowing down. Now, we don't want it to stop, because if it stops, it's going to stop and then come back. So we don't ever want it to stop. But because the force acting on it is the force due to gravity, it is a conservative force. Energy is conserved. Energy initial equals energy final. So the initial energy, well, of course, it's kinetic plus potential, is equal to kinetic final plus potential final. That hasn't changed. Kinetic energy, the formula for kinetic energy is, of course, and presumably you've said it, 1/2 mv initial squared. The potential energy formula, what is it? I'm hoping you said which one. The one associated with the generalized force due to gravity. So it would be this one right here. So minus g, this is right here, this is mass 1 here. G mass 1 mass x over r. And r is the distance from the center. So r would be the distance from here to here. Is equal to, that's r initial, is equal to 1/2 mass of 1 v final squared minus g mass of 1 mass of x over r final. All right, so this is a very similar process to what we've done before. In other examples, this was mgh instead of negative g m1 and 2 over r squared, over r. So now we've got to figure out what we can get rid of. Well, the thing is slowing down as soon as it's launched, and it's never going to stop, but it's going to get closer and closer to zero. So if we go an infinite distance away, then it is going to be infinitely slow. It's still moving, but it's not quite stopped. However, it's close enough for physics. And so, since this is going to, at r equals infinity, the speed is approximately equal to 0 meters per second. And so this becomes 0. This, since the denominator is infinitely large, whatever's on top here, g is a constant, mass 1 and mass of the planet are relatively constant, and so we have some constant divided by a variable. When this denominator gets infinitely large, this goes to 0, because Rf goes to infinity, and this is because Vf goes to 0. And so what we are left with is just this is equal to 0. So we got some space over here. And so I have 1/2 mass times the initial speed squared, and that initial speed is what we're trying to find, minus g mass 1 mass x over the initial radius, the initial distance it is from the center of the planet. Well, if I'm launching it from the surface, this Ri here, this initial distance, is just the radius of the planet. So radius of x equals 0. In other words, and that's mass 1 there, 1/2 mass 1 Vi squared equals g mass 1 mass of the planet over Rx. Mass 1 cancels out. And what we're left here is Vi is equal to the square root of 2 big G mass of the planet over radius of the planet. So we can now calculate theoretically what the escape speed is. Now we are making some assumptions here, of course. One of the assumptions is that when it is launched, the object does not hit anything. It's not hitting any other planets. It is not hitting any atoms in the air. There is no air resistance, in essence, is what we're dealing with here. This thing is launched and doesn't hit anything else, and it's launched directly away from the planet. So now, for Earth, the escape speed becomes the square root of 2 times 6.67 times 10 to the negative 11th times the mass of Earth, which is 5.98 times 10 to the 24th, divided by the radius of the Earth, which is 6.37 times 10 to the 6th. That's meters, this is kilograms, and this is Newton meter squared per kilogram squared. And I'm going to have to edit this part out, and I'm going to go grab a calculator. Unfortunately, my calculator's at home, so I'm going to have to use this piece of crap. Clear. All right. So I have 2 times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 6.37. 6. So this becomes the square root of 125232653.1, and the square root of that is 11,190, I'll just round off, 191 meters per second. So if we could launch something at a little over 11 kilometers per second, then it would, in theory, leave Earth and never return. And there are some things that do this. There are molecules in the air which get hit by radiation and happen to be going the right direction fast enough, and it will escape. We do have atoms leaving the Earth. We also have atoms coming into the Earth because we go through stuff. Space is, we call it a vacuum, and it's close enough for almost all purposes. However, it's not really empty. One other thing, talking about units here, or looking at units. But first, let me extend this just to show that the units work out. One, I'm only dealing with SI units, so speed better be meters per second. But if we take a look at units, I have the square root of Newton meter squared per kilogram squared times kilograms over meters. And so that kilogram cancels out with one of those, that meter cancels out with one of those, and I'm left with a square root of a Newton meter per kilogram. A Newton is a kilogram meter per second squared, so this becomes the square root of a kilogram meter per second squared times meters over kilograms. The kilograms cancel out, and I'm left with the square root of meter squared over second squared, which is a meter per second. So that's the units just matching up there. So at this point, we have a formula right here that we'll be using again in the next video when we actually talk about black holes.